Hello, I am Professor S. Sankaran in the Department of Metallurgical and Materials Engineering. Yes, we are going to just look at the some of the salient features of bonding character. So, one of the primary aspect is the solid state can be visualized as atoms vibrating about their mean positions on fixed atomic sites, and in a liquid state the atoms have also translational freedom, important, and that can slide past one another. The bonds between the atoms in the liquid are continuously broken and remade. This all we know. In gaseous state, bonds are totally broken. The higher the bond strength, the more will be the thermal energy required to break the bonds. Correspondingly, strongly bonded materials tend to have high melting point and boiling temperatures. So, this is something which we also looked at the correlation with the potential well diagram, right? When you have the steeper potential well diagram, it has got something to do with bond strength as well as melting point, right? So, we will again acknowledge this idea as we just move on. Wherever we try to connect with the atomic basis of the properties, we will be able to connect this idea or carry this along. Okay. So, when a solid consists of molecules held together by secondary bonds, the melting and boiling points of the solid reflect only the strength of the secondary bonds between the molecules and not the strength of primary bonds within the molecules. You see, as we just move along, we will see that the external force, or in this case, we are talking about boiling point, and that is a thermal energy, or even when we say force, it's a mechanical energy. So, how these bonds responds to the external forces. So, that is the ultimate point we will reach, right? So, how these primary bonds and secondary bonds respond or resist to the external load, that determines the physical property primarily and then mechanical property as well. Yeah. So, the typical ionic and covalent materials have a good thermal and electrical insulators, right? And solids which have secondary bonds such as van der Waals bonds are also good insulators. This is true because most of the ceramic material, they are all mostly covalently bonded or ionic bonding, or it mixture of these two characters together, like intermetallics and so on. So, the thermal expansion of materials arises from the asymmetry of the potential energy versus distance curve. Deep potential wells are more symmetrical about their equilibrium positions or not than the shallow potential wells. So, the thermal expansion at a given temperature tends to be less for strongly bonded materials than for weakly bonded materials. So, this aspect we will look at it in much more detail in the coming lectures. So, the thermal expansion of material arises from asymmetry of potential energy well, that we have already discussed yesterday by looking at the geometry of this nature of the curve. Okay. So, we will connect them by giving examples in the coming lectures. Okay. So, these are some of the important salient features about bond characters and properties. So, finally, what we are trying to say is the mechanical properties of solids are dependent on strength of bonds as well as directional nature of bonding. Solids with the strong and directional bonds tend to be brittle. For example, covalently bonded diamond is very hard and brittle. So, having connecting with all the physical properties, we are now saying that mechanical behavior of materials also strongly dependent on the type of bond and its nature and also directionality and so on and so forth, right. So, I was just mentioning in the initial part of the bonding, not necessarily all covalently bonded materials will be hard but there is another requirement, right. So, the covalently bonded materials will also have a uniform surroundings as in the case of diamond. Even in polymers you have a covalent bond, but then the first line of resistance is not the primary bond covalency there, but there it is a van der Waals forces which takes the initial load. So, the response of the material is quite different as compared to diamond type of materials, right, where you have a covalent bond is uniformly are surrounded by all the atoms, all the neighboring atoms have this same covalent bond. So, it is so hard and strong, and mechanically it is brittle in fracture, right. So, as metallic bonds are relatively weak and non-directional, metals are soft, ductile and malleable. They can change their shape permanently without breaking. Ionic solids fall in between covalent and metallic solids in that they may exhibit a very limited amount of ductility. So, you have one extreme metallic bond and the other extreme is covalent bond. Ionic bond comes in between in terms of their mechanical strength and the physical properties. So, now we will see some of the examples. Suppose if you take metals and alloys and they exhibit metallic kind of bonding, and most of them are polycrystalline. So, the crystal grains they consist of, the microstructure consists of crystal grains, and advantages they are very strong, stiff, ductile and conductive. Disadvantages they may not have very good fracture and fatigue properties, that could be any limitation. And if you take polymers, they are all covalently bonded as well as secondary bonds. The microstructure will show that these materials consists of chain molecules, or the microstructure completely contains a molecular chain folded into some crystalline form or entangled form or tangled form and so on. Advantages in terms of utility, low cost, lightweight and very importantly corrosion resistant, right. So, disadvantages from the engineering point of view, low strength, low stiffness, do not have a good creep properties. Okay. We will see, we will understand why these things are so as we proceed further. If you take ceramics and glasses, they are having ionic bond or covalent bond or both. Okay. They could be polycrystalline nature or there could be semicrystalline or amorphous in nature. Both state of microstructure is possible. That could be completely amorphous or semicrystalline and so on. Advantages, they are strong, stiff, hard, resistant to temperature, very important property, and resistance to corrosion, this is again very important property, very attractive property from the engineering point of view. Disadvantages, they are highly brittle. Okay. And finally, composites. Bonding could be of various combination in nature, because a composite can be made up of any 2 or 3 material together. Each one may have a different bonding, right? It could be covalent and ionic, or for example, if you take fiber reinforced plastics could be, having bonding of covalent and secondary bonds, and your reinforcement could be ceramic, or it could be metal, or it could be fiber, depending upon what type of reinforcement one wish to add. So the bonding is various type of bonding possible. Microstructure, either there is a two constituents, major constituent here. One is matrix, another is reinforcement. So matrix can have one microstructure, fiber or reinforcement will have some other microstructure, and so on. The advantages, they are very strong, stiff, and light weighting, very importantly. Disadvantages, very high cost, and they may lose their the togetherness by delamination. That fiber will pull off, or it get delaminated from the matrix. These are the properties which will deteriorate the mechanical behavior and so on. So you see that this table clearly demonstrates that there is a strong connection between the chemical bond of a material and what kind of mechanical property they exhibit. Okay, there is a strong connection. So that is the reason we are looking at chemical bonding much more closely. So the next important subject I want to just go and review, like chemical bonding, though we all know that. A similar thing, subject is strength of materials. So we will just review this before we proceed further. What is strength of materials? The subject deals with relation between internal forces, deformation, and external loads. Okay. So assuming the members are in equilibrium, that is static equilibrium, the equations from the static equilibrium are applied to forces acting on some part of the body in order to obtain a relationship between external forces acting on the member and the internal forces resisting the action of external loads. You see, we want to have some design criteria. Okay, so let us assume that you take a material which is assumed to be in an equilibrium. In the strength of material concept, the static equilibrium equations are applied. So when the external force act on the body, then the internal forces will resist them. So basically the internal force resistance is termed as a stress, right? The resistance to external force in terms of internal resistance. For example, here we talked about primary bond, secondary bond, and so on. So all these bonds will resist the external force, right? So that external force will be resisted by internal force, so which is termed as a stress, right? And then we need to look at the stress distribution in the body, whether it is acting in a point or it is where all it is distributed. But the very important point is, you just look at it. So the internal forces, that is resisting forces, are usually expressed by stress acting over a certain area. Okay. The stress distribution is arrived at by observing and measuring the strain distribution. So this is important. So we are not going to measure the stress directly because it cannot be physically measured. Stress cannot be physically measured. So, we are looking for a strain distribution, and we will measure the strain distribution by what? The strain distribution, the strain, we will just look at it, how we are going to measure the strain through some displacements, right? How from the displacement, how experimentally we will be able to measure the strain, that we can see. See, the important assumption in strength of materials are that the body which is being analyzed is continuous, homogeneous and isotropic. So, we should know the meaning of these three words, and a continuous body is a one which does not contain voids or empty spaces of any kind. A body is homogeneous if it has identical properties at all points. A body is considered isotropic with respect to some property when that property does not vary with direction or orientation. So, directional nature. Okay. So, what strength of material try to do is it makes some assumptions basically, like the material is continuous, homogeneous and isotropic and so on. Okay. And then it try to apply the static equilibrium equations where a body is subjected to an external force, and the resistance from the body, the internal forces, is being measured as stress. But then, as I just said, stress cannot be experimentally physically measured. So, we look at the deflection or displacement, then we measure a strain, and we have the constitutive relations between stress and strain. The most popular one all of us know is Hooke's law. Okay, stress, it states that stress will have a linear relationship with strain and so on. So, they are all called constitutive relations. From this constitutive relations, we try to calculate the stress, and then from the stress we try to calculate the load and the dimension of the member, and which will be based upon the material property or mechanical behavior of materials. So, this is the, in a nutshell, the strength of material philosophy try to give. So, it is very useful, right. So, as a design engineer, if you want to select a material, okay, if these properties are given or these relations are given or something is known, so you will be able to calculate the loads and the dimensions of the material depending upon the specific applications, right. So, so that is philosophy of strength of materials. So, with this background, we will just try to move further. We will look at again elementary properties, elastic and plastic behavior. So, what is shown in this figure is a cylindrical bar which is fixed at one end and which is subjected to an axial load, okay, in this direction, that is a P, axial load P. And you can see that there are two points which is referring L0, showing the initial position. Then after you pull this bar to some extent, then these 2 points move to the new positions, which is the distance between the two new points will be L0 plus delta. So, what is delta? Delta is the deformation, right. So, you should also think about, suppose if you try to pull this rod in this direction, the length increases, also a corresponding a diametrical reduction is also expected, right. Okay. So, that is a kind of configuration we are now trying to look at and describe. So, the word average linear strain E, okay, um, is measured here, and delta is the deformation, the slight increase in the length and a decrease in the diameter. That is what trying to show here. So, it can be written like this: the average linear strain is equal to deformation delta divided by original length L naught, or change in length by original length can be written as L minus L naught by L naught, that is linear average strain. And what is shown in this diagram B is a free body diagram, where again um, the member is being pulled in this direction P, and against its internal forces, it's shown in this kind of small lines, and this is an external load P. That is what is written here. The external load P is balanced by the internal resisting force, this force, which can be an integral of the internal force, resisting force, times the area. So, area is dA, this particular area. So, the equilibrium equation for this particular free body diagram is P is equal to integral sigma dA, okay. And if the stress is distributed uniformly over the area A, if sigma is constant, then we can say P is equal to sigma integral dA is equal to sigma A, or sigma is equal to P by A. So, this is how the stress is being defined. And very important thing is, the stress will not be uniform over the area A, therefore, the equation represents average stress, right. So, this is what you have to be careful. So, here also we just use the word average strain, here is average stress. So, that means okay, when you take a body or a member which is being pulled in one direction or subjected to an external load, the strength of materials concept or continuum assumes that every point of the body undergoes a similar or every point of the body experiences similar load or similar force, okay. But that need not be the case in reality, right. So, it could be, there could be some part will undergo more stress than the other. So, we do not have that clarity there. So, that is why it is called average stress, right. It is not stress, the stress is not going to be uniform all over the body, or even the strain is not going to be uniform. That is why it is called average strain, average stress. So, this we have to keep in mind. So, when you talk about body in equilibrium under the action of external force, there are two kinds of forces. One is surface forces. What is surface forces? Hydrostatic force, pressure exerted by one body on the other, okay. So, we are saying that external force on a body, right. So, what kind of force? So, that could be two forces. One is surface forces. What is the other one? Other one is the body forces. What are body forces? A body forces which is distributed over a volume of a body. Please make a note of it. This is over a volume of the body. Something like a gravitational force, magnetic forces or inertia forces, they are all called body forces, right. So, in engineering, two most common type of body forces are encountered. One is centrifugal force due to high speed rotation, and the forces due to temperature differential, that is thermal stress. These are all two most common type of body forces which is encountered in the engineering applications, right. So, now we will see how to look at the concept of stress at a point, right, as per the strength of material concepts. So, look at this diagram, which is a body which is assumed to be in equilibrium is subjected to external pressures P1, P2, P3, P4, P5. Okay. And then we are interested in looking at the stress at the point O in the plane mm. Okay. So, you can say that this plane mm is bisecting these two parts, part 1 and part 2, and this is a x, y, z coordinate. Okay. So, as per the strength of material description, so what we can do is we will cut this plane, cut this body into two, and then what it means is the part 2 comes off from this, and then we are interested in measuring the stress at a point O, which is taken from the whole body like this. What it means is, the removed portion of the body is replaced by the resisting force or external load at this point or at this area. Okay. Or otherwise, whatever the forces which were there when these two parts were together, it's assumed to be still there, and we are interested in looking at the stress at a point O. So, take area delta A surrounding point O, and delta P acts on this area because of this external load. If delta A is continuously reduced to 0, the limiting value of the ratio delta P by delta A is the stress at the point O on the plane mm of the body 2. So, it is a limiting value of the ratio delta P, that is limit delta A tends to 0, delta P by delta A, which is nothing but as sigma, that is stress at a point according to strength of material concept. So, that is one way of looking at the stress at a point, how to visualize or how to grasp the idea. Okay. So, what are the types of stresses we know? Like if you look at this diagram, so you can just assume that this is the same cross section mm in the previous diagram. So, the sigma what we refer is a total stress that can be always resolved into two components, a normal stress sigma which is perpendicular to the area of cross section or the area of interest where we define the O, the origin of the point, and the shear stress tau lying in the plane mm of the area A. Okay. So, what is the same coordinate is given here. Assume this plane is in mm, and this is the P, OP is a similar direction of the load what is given. So you can see that this plane OP is lying in O, Z and C, this kind of a plane, this vector basically. And we now say that sigma, the normal stress, is equal to P by A cos theta. So this is P and this is the angle between these two. So we are looking at a normal stress, that means it's a normal to this plane. So it will have this theta component. So that's why it is P by A cos theta. And the shear stress will be in the plane acts along OC. So this is the angle between y and this plane, that is phi. So tau is P by A sin theta. So this this theta, and we are looking at the shear, and it may be further resolved into two components parallel to x and y direction lying in the plane. So the shear stress can be further divided into two, that is because of this projection. So P by A sin theta is shear stress, and P by A sin theta sin phi is a shear stress acting in x direction, and P by A sin theta cos phi is in y direction. So this is just a very convenient way of resolving this, the stresses, and this is the way to look at it. So when we have a total stress, you should remember that it is always convenient to resolve them into a shear stress and a normal stress, right? So this is a convention which is being followed. So I thought first I will introduce this, then before we get into this next one.